In this video, I want to talk about how we usually measure voltages and currents in uh, electric circuits. So an ampermeter or an ammeter is an instrument that is designed to measure the current that goes through the individual components of a circuit. So ammeter is placed in series with the circuit element that we want to find the current for. Do you know why we place the ampermeter in series with the element? If you remember from KCL, we said that if we have two components that are connected in series, the current that goes through them is equal. So let's say we want to measure the current that goes through R1. So we have I1, I assume it in this direction, and then I place the ampermeter or ammeter in series with it. So let's just assume that the current that this one is going through it or measures is I2. So since we have this node common between the two, we can easily write the KCL for this node. So if I write the KCL for this node, we have negative I1 because I1 is entering the node, positive I2 because I2 is exiting the node, equals 0, which means that I1 equals I2. So that is the reason that we place the ampermeter in series with the component for which we want to find the current to. On the other hand, a voltmeter is an instrument that is designed to measure the voltage of a component. And as opposed to ampermeter, a voltmeter is placed in parallel with the circuit element for which we want to find the voltage for. Why is that? Again, if you remember from previous lectures, when we have two components that are connected in parallel, so basically they share a pair of nodes, the voltage across them is going to be equal. How we can get that? We can easily use the KVL to do the analysis. So this thing is left for you. So let's just say we are connecting this into a voltage source here. So if I write the KVL for this loop, the conclusion is that V equals V1. If I write it for the second loop, the conclusion is V equals V2, which basically means that V1 and V2 are equal. So to measure the voltage across R2, we place the voltmeter, this figure, in parallel to R2. So as you can see here, when we measure the current or when we measure the voltage, we are practically adding an additional element to our circuit. So what is the effect of this additional element in our circuit? So ideally speaking, an ampermeter should have an equivalent resistance of 0 or should function as a short circuit. So the effect of the ampermeter to the circuit is minimal. So let's just say we have R1 here, and let's just say we have this equivalent resistance for this ampermeter. So if we want to find the equivalent resistance of these two components, the resistor and the ampermeter, who are in series, we have the Req to be R1 plus Ra. So the more Ra is closer to 0, the more Req will be equal to R1. So the less resistive resistance, the less resistance that the less resistance the ampermeter has, means that the less effect it has on the circuit itself. So practically, we consider the ampermeter to be equivalent to a short circuit or a simple wire. What about for the voltmeter? For the voltmeter, let's just say we have this equivalent resistance for the voltmeter. I call it RV. And what is the equivalent resistance of R2 in parallel with RV? So we have Req to be R2 RV divided by R2 plus RV. So if you remember from before, when RV is very large or goes to infinity, Req for the two resistors that are in parallel will be R2. So ideally speaking, a voltmeter has an equivalent resistance of infinity, or effectively it can be considered as an open circuit. So these are the ideal cases. In reality, these are not usually the case. So the resistance of an ampermeter is not zero, but is very close to zero in comparison to the other components that we will use in our circuit. And also the resistance of a voltmeter is not practically infinity, but it is very large in comparison to the other components that we generally use. So now that we saw this, let's just quickly go over the two types of meters that we usually use. We can have digital meters and we can have analog meters. So a digital meter has a shape something like this. Of course, different brand, different digital meters have different functionalities. But generally speaking, a digital meter measures the continuous voltage or current signal at discrete points in time. Basically, it samples the voltage or the current, and then it converts it from an analog signal to a digital signal and then displayed. In general, a digital meter is more ideal and easier to connect and is more precise. And it is very common in practice nowadays. On the other hand, for analog meters work based on the Darson voltmeter movement, in which we have this permanent magnet here. Between these two sides of the permanent magnet, what we have is a magnetic steel core, a restoring spring. Basically, whenever we are not using this, it basically puts it in at zero position. And then we have some movable coin that when the current goes through these coins, as a result of the interaction between the magnetic field of the permanent magnet and the magnetic field that is created by this current in the coil, we have some movement. That movement represents the amount of current, for example, that goes through the coil. So as I said, in practice, we usually use the general meters nowadays. So in this video, you got introduced to ammeter or ampermeters. Also, you saw voltmeters. You also learned how you can connect an ammeter to measure a current in a circuit element. Also, you learned how you need to connect a voltmeter to measure the voltage across an element. And also, you got briefly introduced to digital and analog meters, and you saw how they perform.